Yeah, can you see my screen?
Yes, sir.
Sir,
Yes, sir.
is it affine set always convex?
Yeah, no, an affine set is always going to be convex. So,
I mean, they are same.
sorry?
Affine set and convex set, they are same. I mean,
No,
they
no,
are seen.
no, they are not same. So this is the way you want to think of it. Every affine set is convex, but not every convex set is affine. Affine sets are going to be unbounded. Recall that what were affine sets? We had this equivalence, right? Affine sets are precisely translates of linear sum.
Yeah, I got it, sir. Sir, one way it is open. I mean, from one side because we have range.
Yeah, right, right. So, so those are rays, for example, are convex sets, but they are not affine, as you said.
Yeah, got it.
Mhm.
Thank you.
Okay. So, yeah, just to remind you what we have been doing, like we have been talking about a decision space, and in the previous lecture, what we did was essentially finish our discussion on like affine sets, convex sets, and this convex cones, which define the notion of positivity. And based on that language, we could rephrase our decision space in this manner. It is the set of all these vectors x, such that ax is less than equal to this vector b. The x and b are not necessarily of the same dimension. Um, and you had cx equals d. And this was the affine set. It is unbounded. And here, this was a convex set. This determined a convex set. And to write that equality, for this, we needed a convex cone. So it made our like language much simpler to do it that way. And from all this, of course, then we started talking about examples of convex sets. And the main examples I mentioned, the building blocks of any convex set, although we have not proved that so far, but I mentioned that any convex set is in fact intersection of half spaces. So that's why hyperplanes and half spaces are important. Um, and then the other examples we saw were polyhedra. So those were half spaces were essentially the outcome of one non-trivial linear inequality. So one non-trivial linear inequality, and hyperplanes were obtained from one non-trivial linear equality. But if you took like bunch of half spaces and hyperplanes, so polyhedra, finitely many linear equalities and inequalities and linear inequalities. And this was so we are essentially, we found some language to talk about our decision space. So here we observed that in linear programming, our decision space is a polyhedron. And then we had this polytope, a bounded polyhedron was called a polytope. For example, half spaces are polyhedral. Hyperplanes are also polyhedral because finite also includes one equality, that's also finite. So half spaces and hyperplanes are examples of polyhedral, but they're not examples of polytopes because they're not bounded. And typically we want this sort of boundedness because we want to say that, okay, the optimum exists for our objective function. Like typically for LP, we have linear objective functions, but in general, let's say you're talking about other sort of smooth functions. If you have a compact set, you know kind of the maximum and minimum are attained. So you would also like to know conditions based on this A, B, C, D, such that what you get is actually a bounded set. Yeah. These were the main examples we talked about: half spaces, hyperplanes, polyhedron, polytope. And then we started with one basic result called Carathéodory's theorem. So just to remind you, essentially it said, Carathéodory's theorem said if you have a subset S of Rn and X belongs to convex hull of S, then X is a convex combination of affinely independent points of S. Convex combination of affinely independent points of S. And there was a small question by Ramakrishna that in the proof, when we started off, we had this assumption that there are affinely dependent points, so that we can write it as a right? X has a linear combination of those affinely dependent points. So the question was, how do we know such things exist? There are affinely dependent points whose linear combination is X. So the answer is simple. If there is none like that, then you're done, right? Already X is a convex combination of some points of S. If they're not affinely dependent, that they are affinely independent. So the theorem is done. So otherwise, what we did, we chose a minimal set such that X is summation lambda I xi, I equals 1 to k. So k was the smallest such number so that all these lambda i's were strictly positive. So there we showed that these xi's must be affinely independent. If not, we obtained a contradiction. So that was the strategy of the proof. So I hope that is clear. All right, and from this we derived that any convex, like the convex hull of any set is in fact union of simplices or simplexes whose vertices are located in S. So that was another example, another special case of a polytope. Simplices, in fact, K simplex is an example of polytope. It is bounded and it can be determined by a number of equalities and inequalities. I had mentioned that you can talk about this equality, x1 bigger than 0, xk bigger than equal to 0. So this will determine a simplex, a K simplex. For example, if you had k equals 2, x1 plus x2 equals 1, x1 equal bigger than equal to 0, x2 bigger than equal to 0, just determines this region. So this is that line, and this is the positive orthant or quadrant in this case. So this is 2 simplex. So similarly, for the K simplex, you can give such a description. Okay, so and that's an example of a polytope. So the last thing we had talked about, we had just given an indication, is what we care about is representation theorems for convex sets, closed convex sets. So just like when I talk about linear spaces, we said, okay, basis is good enough. Finitary information, it's like a generating set, a finite generating set for the whole subspace. And similarly for affine sets, for a K
Sir,
dimension. Yeah.
sir, in the previous corollary that you stated that K simplex one, we can tell that it is the union of all simplices with the vertex on the
Yes.
points, affinely independent points. But how are we telling that? I couldn't understand it.
Okay. So essentially what we have shown, so what I want to say is S is union of all simplices in S, right? This is essentially what I'm claiming. So given any point in X, I want to say there is a simplex consisting of vertices of S such that X belongs to, so so given X in S, or rather convex hull of S, I want to say X belongs to some simplex with vertices in S, right? This is what I want to claim.
Yes.
What I've shown is X is a convex combination of affinely independent points of S. So take those points. So these are affinely independent. What was definition of a simplex? It is the convex. So a K simplex was the convex hull of K plus 1 affinely independent points, right? So essentially what
Okay, sir. I
yes,
got it.
yeah, right. So you choose those affinely independent points, generate that simplex. So X belongs to that simplex, and it might change. Like depending on X, these points might change, but it is in some simplex. Okay. So, and visual example I mentioned, typically that will be the case for polytopes is if you have this interior of this pentagon. So these will be like the simplices. So you give me any point in the pentagon, it has to lie here, here, or here. And in each cases, each of these triangles are simplices. So is each of these three, they're simplices. Okay. Yeah. So coming back to the last thing we had talked about in the previous lecture, it was about representation theorems for closed convex sets. So we said there are two ways to do that. So anyway, by representation theorem, I mean, I want to give certain building blocks and a way of combining those building blocks to generate a general convex set. So representation theorem 1, this hopefully we will be proving today, finishing it off. The other theorem we may not be able to. So representation theorem 1 said that for each non-empty closed convex set in Rn is the intersection of its supporting half spaces. So we have not defined what a supporting half space is, but intuitively I said what that means. Like you have some convex body. So at this point, you have some sort of hyperplane which is tangential. Convex sets will typically have positive curvature. I'll put that in quotes because I've not defined what curvature is, but intuitively you can imagine that. So these are like the supporting spaces. So on one side, the convex set completely lies, but on the other side, there is no part of the convex set. But that needs a proof, of course. So we will do that. But if you are willing to intuitively take this, essentially it says that each non-empty closed convex set is the intersection of its supporting half spaces. So half spaces were examples of convex sets. So I said these are the building blocks, right, in representation theorems. So how am I combining the building blocks? I'm taking intersections. So that is how I'm building up convex sets. And these half spaces are given by linear inequalities. So if, for example, if you had a polytope that by definition was given by finitely many, or polyhedra, it was by definition given by finitely many linear equalities and inequalities. Here you're saying, in fact, any closed convex set can be done that way. But the only difference might be you may need infinitely many. Okay, so these are the building blocks. Half spaces are the building blocks in terms of representation theorem 1. In representation theorem 2, our building blocks will be certain things known as, at least in the compact case where the convex set is compact, the building blocks will be extreme points. And the procedure, how you will build, is take the convex hull. Here the procedure is taking intersection. There the procedure is taking convex combinations. So anyway, we'll come back to representation theorem 2 later. But for now, this is our target. So if we finish this by end of today's lecture, we'll be happy. Okay, so we have to start with these definitions of supporting half spaces and so on. Now let S be a subset. I'm not talking about any structure or convexity or anything like that. Let S in Rn be a subset. Okay, I mean, that's the notation, but I'm just rewriting it in words. I want to emphasize that there is no extra structure on S. And H equals HAB. This was the notation we used for hyperplanes. Be a hyperplane. Okay, and as usual, and let HAB plus and HAB minus, recall HAB minus was governed by A transpose X being less than equal to B. So that was the half space, and here it was bigger than equal to B. And the intersection of these two closed half spaces was this hyperplane. Okay. So, and let HAB and AB plus and HAB minus denote the two closed half spaces bounded by HAB. Okay, so here comes the definition. So this was just notation. So we say that H, which again, like here we're describing using AB, but if I just said a hyperplane, I would just say say that this hyperplane H supports the set S. Supports S at the point X if, first of all, X has to be in S. So when you support, you have to be like at least intersect your set. So if X belongs to S intersection H, and either this set S is completely contained within this positive thing, or S is completely contained within this negative half space, or so one of these closed half spaces. So you can imagine I have this hyperplane and I have a region defined here and I have a region defined here. So this is HAB plus, this is HAB minus, and I have a point X here. So the set is somewhere here. So I will say this hyperplane H supports S at this point X in S if, first of all, that point also belongs to that hyperplane, and this whole of set S belongs to one side of that hyperplane. So that is why it is supporting. So that is intuitively clear why we need such a definition. So on the other side, no part of S is in there. Okay.
Sir, please describe the figure 1 second.
Please differentiate.
Describe the figure. I mean,
I didn't understand that word. Deframe.
describe.
Oh, describe that figure. Okay. Yeah, let me describe that again. So let's say you start with some S. Maybe it's a discrete set, maybe it has some structure. And this is a point X. So this is S, this is a point X. So I will say a hyperplane is a supporting hyperplane at X if first of all it contains that point X. So this is a hyperplane. So it has to contain X, and at the same time, this whole set S is on one side of this. So this is H. S is on one, so S is located completely on one side of H, or one of the half spaces. So the fact that H determines two half spaces is clear, right? So you have one, like it splits your whole Rn into two parts. So a hyperplane will be said to support S if S completely lies within one side of H. To give you an example where it is not a supporting hyperplane, that would make it clearer, I believe. So let's say I take these 3 points. That is my S, and this is my point X. If I, and in 2 dimensions in R2. So this is R2. And I draw this line. Hyperplanes are supposed to be lines in R2. Now this is not a supporting hyperplane for S, right? Because this set S is located both within this side, this half space, and also in this half space. So it is not completely on one side. So that is not a supporting hyperplane. So not a supporting hyperplane. So in that same example, what is a supporting hyperplane? So I'll take these 3 points, that is my S. If I take this line, then all of S, every point in S is on one side of this line. So this is actually example of a supporting hyperplane of S. So just imagine the same happening in higher dimension. And this is just a definition. So there is nothing to really prove or justify, except that intuitively you should think you have a set S and you have a point potentially on its boundary. If you don't take on its boundary, the hyperplane will always split it up. If you take a point in the interior of S, then if I take any hyperplane here, there is a ball which has dimension n, right? Hyperplane has dimension 1 lower. So there's no way to have a supporting hyperplane passing through a point in the interior. So in general, you will always have to look at boundary points, and a supporting hyperplane will be like tangential there, so that everything, like at least for convex sets, everything will lie on one side. If it is not convex, for example, if I have something like this, then if I take a point here, there will not be, so this is in R2 again. So you'll not find any supporting hyperplane at this X, because any line I draw has to intersect. Like if I draw this line, part of it is here, part of it is on the other side of this line. If I draw something like this, again, part of it is here, part of it is here, and so on. But if I drew something like this at this X, if I draw this tangent, the whole set is lying on one side. This side, there is no part of this body. So I hope it makes it clear. Can you please confirm that this was clear?
Yes, sir.
Okay, great. Yeah, so that was the definition of H supporting S. But we'll also use other words to describe H. So H supports H, that was like in terms of a verb, but we'll also use a noun for H. So H is a support plane of S. So those two mean exactly the same. So is a support plane of S, or H supports S, or you can say S is supported by H, and so on. Okay, so H is a support plane of S or supports S if H supports S at some point which is necessarily a boundary point of S, which is just what I mentioned, which is necessarily a boundary point of S. Because if it is an interior point, no matter what hyperplane you take in there, the ball around that, however tiny it might be, it will be split in half, and one half will lie in the HAB plus and the other half will lie in HAB minus. So there's no way to do that. Okay. All right. And so this was about supporting planes. And you can imagine similarly, there is a supporting half space. So supporting half space will correspond to the supporting plane. And it is the space which will contain that the set S. So let's just clarify this definition. So if HAB supports S and S is completely contained in HAB minus. I mean, by definition, if this supports S, S is either in this minus or this plus. So if S is contained in HAB minus or HAB plus respectively, then HAB minus, HAB plus respectively. By respectively, I mean you can just substitute this HAB minus with HAB plus and the statement will still hold true. So this is called a supporting half space of S. Supporting half space of S at the point X. And A, so here I will not use the word respectively. Here I mean particularly in the case of HAB minus. So A will be called an exterior or outer normal vector. So I'll clarify this point. So you have this object like something like this. Here you have a point, and this is the supporting hyperplane, and this is the supporting hyperspace. This whole half space. So how is this half space defined? You have this vector A. So it is essentially given by something like this. All those vectors X such that A inner product with X is less than or equal to B. So in that case, the vector, so when I say A dot X is less than or equal to B, I mean, and of course I can always translate things and say A minus AX minus X dot X naught is less than or equal to 0. So you just find one point where A dot X is equal to B, and this is what you can do. Now, when is the inner product of two things less than or equal to 0? That is when the angle is more than 90 degrees, right? From 0 to, of course, here the angle can only be like 0 to 180. It cannot be more because then you'll be winding around. So cosine theta, so that is the term like determining sign of this inner product. Cosine theta will be negative if and only if theta will be between 90 degree or 180 degree, or if in radians pi over 2 to pi radians. So now if this is defining this half space, this A has to point outwards. So A points outwards to the half space. So this is X naught. Okay, then I'm using two arrows. So this is actually the normal arrow, and this is to, okay, let me just use a red line. So this is X naught. This vector right here is X naught. So X minus X naught is essentially these vectors. All these X's are lying in this half space, right? X minus X naught is this vector. So when I'm saying A dot X minus X naught is less than or equal to 0, I'm just saying that these are more than 90 degree away. So from here you can easily see A points outwards, not inwards. There are only two options. Either it points out this direction or this direction. But in this case, we are clear that A points outwards. So that is why I said this forget about the respectively part. That only holds up to here. It's called a supporting half space at X. And A is called an exterior or outer normal vector in case S is contained in HAB minus. So A points outwards. So I hope that picture is clear. All right. So yeah, so that's the exterior or outer normal vector. So that picture I hope is clear now. Okay, so with this definition, we'll also build some new tools, because remember, our goal is to prove representation theorem 1. So here we are already seeing that like for convex sets, so for example, this square. So if I look at this hyperplane, this hyperplane, this hyperplane, and this hyperplane, and think of these as the outward normal vectors, that means the negative half space is, for this it is this space, for this it's downwards, for this it's upwards, and intersection of 4 of these will just give me this. So the supporting half spaces generating the convex set, that is intuitively clear, and we want to rigorously prove that in general. So for that we need this tool, very natural tool called metric projection, and one should be very careful when looking at this, because this, you will also see it in your analysis 4 when you talk about Hilbert spaces, like convexity properties in there. So like yeah, so this is actually useful much more beyond the context of proving representation theorem 1. Okay, so let's look at this definition. So first, K here we are saying is a fixed non-empty closed convex set. So this is the notation we'll be using throughout. So it's a fixed non-empty closed convex set. Okay. So first we have a lemma. To each vector x in Rn, there is a unique point. There exists a unique point P, K, X. So that's the name of that point. I'm going to describe what like defines this point. Satisfying X minus, recall, there's a unique point in K, in that fixed non-empty closed convex set K, such that X minus P, K, X is less than equal to X minus Y. So this norm is Euclidean norm. So this is just saying distance between X and PKX is less than equal to distance between X and Y for all Y in K. That is, so in words, there is a unique closest point. So that is, there is a unique closest point in K from X. For example, if I told you something like this shape. So this is a circle. Think of this as a part of a circle with center here. So this is not a convex set. Here you have, so, and let's call this K. So in that case, there are many points which are closest to this point, right? This point is closest, like they have the same distance. But for convex sets, that cannot happen. So if I have a convex set like this, and I have a point outside it, if it is inside, the closest point is itself. So if X is already in K, then the closest point in K to X is just X itself. So nothing much to do there. So it's the unique point. But if X is not in K, it's outside K, then there is a kind of unique point here, which is closest.
We can prove it by contradiction.
Yeah, I mean, essentially the proof will proceed that way, but how do you build that contradiction? Do you have an idea?
Like if I take that, let's say that there are 2 points which are closest to X, and those 2 points lie in the convex set. So their middle point should also lie in the convex set.
Right, exactly.
And so that should be even closer.
Yeah, so this is just purely thinking Euclidean geometry. Let's say y0, y1 are 2 such points. Then this is an isosceles triangle, right?
Yeah.
So this is my X, and y0, y1, they are both in K. So this is an isosceles triangle, and this is supposed to be the minimum. But by convexity, all this line also lies in K. And if I take the midpoint, I have the altitude. And altitude is always going to be the smallest distance. So I have found another point, which is actually closer than y0 and y1. So who gave this answer?
Ramakrishna.
Ramakrishna, okay, great. So that is essentially the crux of the proof. But there is one minor point remaining. How do you even know that there is a like smallest point? Like if there are 2 parts, existence and uniqueness. So once you have existence, uniqueness is proved this way. You have to say, okay, if there are 2 points, y0, y1, which are closest, you just draw this isosceles triangle, it's done. So how would you go about for existence? So yeah, let me just formally write it
We
down.
define
So,
a function infimum of all the distances,
yes, you
and
define
that
the
has to attain a minimum in the closed set,
yeah.
compact set. Yeah.
The problem is we have assumed closed, not compact. So there is so it's almost correct, but okay, let me write out the uniqueness part. So there are two parts, uniqueness and existence. So first, uniqueness, just proof you can draw a picture, or of course, like mathematically, we are not. It's not a rigorous thing to put it this way, but that's the main idea. All you have to do is write out the triangle inequality and do such things. Like if so, essentially, you would like to say something like this is less than equal to, so write x as x plus x over 2. So this will be less than equal to half of x minus y0 plus half of x minus y1. And these are supposed to be both the closest points. So they're in fact the same. So this is nothing but half of x minus y0. But then you just show that this distance is going to be less than this distance. So that will prove uniqueness. So you cannot have y0 and y1 being distinct. So these both, this has to be equal to y0, has to be equal to y1. Now existence, as someone pointed out, is first of all, you can define a distance function from x to a closed set, right? So you want to define a distance as infimum. So you take, so this is k, possibly unbounded, possibly infinite. It can be a hyperplane and so on. Those are all closed convex sets. But yeah, but the problem is like, how do you, from that, typically what you do is the infimum is attained or something like that. You want to say something like that. And if k is compact, you can say that the infimum is attained somewhere. And if the infimum is 0, the x has to lie within that set. If it is not, then there has to be some finite distance, however small. So for that, the key observation, quick observation is this. Distance is all about looking at balls, right? Like if I'm saying x and y, essentially I'm taking a sphere. What is the smallest sphere which contains this? So now what I will do is take a sphere which intersects k. So choose rho bigger than 0 such that the ball, so bx centered at x of radius rho, intersection k is non-empty. So you can do such a thing because you keep increasing rho. At some point it has to intersect, otherwise k is empty. So basically from the fact that it's non-empty, you have that. So now look at this region, which is the intersection of b, x rho and k. That has to be compact, right? Because this ball is compact. So b, x rho intersection k is compact. So there you can use that argument that this function, which is a distance of x from this bx rho intersection k, is continuous and is continuous and attains its minimum at some point in this set, attains a minimum. So I should say continuous where? So this is continuous on this compact set bx rho intersection k and attains a minimum. So there is a point here which minimizes this. Here x, think of x as being fixed. Okay. And it is clear that every other point has to have distance more than rho, right? Whatever point you take has to have distance more than rho. So anyway, like as a global infimum, the rest of the points don't qualify as candidates. And here another fact we used was bx rho is convex. That also you can prove using triangle inequality. So Euclidean norm is a norm. It satisfies triangle inequality. So you have two convex sets. Bx rho is convex, k is convex and closed. Bx rho, by the way, is compact. So intersection of a compact convex set and a closed convex set again will be a compact convex set. So that finishes the proof. So any questions? Okay. If not, a quick corollary of this is you can choose k. So to every hyperplane, there is a projection, like there is a closest point. So you can choose, so corollary will be to each x in Rn, there is a unique point say pH of x in Rn in H, which is closest to x. So here H is a hyperplane. So hyperplanes are convex, right? They're closed convex sets, in fact, because they're given by a linear equality. So that's why it is a closed convex set. So based on the previous theorem, you have a unique point. So this will help you to define a projection mapping from vector x to this hyperplane. And like in Hilbert space theory, projections play a big role, projection operators and so on. So there also the proof is going to be very similar, like modulo some changes, but the idea will be using this isosceles triangle for uniqueness. Okay. So this is this function that we define, pkx. So given x, pkx is the point in k which is closest to x. So pkx, so let me write that as a definition. The mapping pk dot. So I'm going to replace the dot with the vector x. So from Rn to k. Of course, this function always takes value in k because it is finding that point in k which is closest to x. Yeah, so this is called the metric projection. Metric projection or nearest point map. Metric projection or nearest point map of k. So it's, by the way, this function is over all of Rn, but its image set, its image is actually equal to k. And for x in Rn minus k, so outside of k, so whenever it is in k, it is actually a constant function. So if you take a point in k, it will map to itself. So for a point outside of k, we denote the vector given by x minus pkx. So geometrically, we will see what this is trying to tell us. So you have this convex set k. Here is a point x. This is the closest point. This is pkx. So what is x minus pkx? That is precisely this vector. So this is x. So this right here is pkx. So x minus pkx is this vector, and we are dividing by this distance to normalize it. So this is the unit normal vector. So unit vector pointing from pkx to x. Okay, I mean, if it was like a smooth convex set and all that, this is precisely going to be the unique normal vector. But if it's a polyhedron and you have these pointy edges, you can have many such normal vectors. But through that point, you'll have a unique one. So that unit vector we're denoting by ukx. Okay, and another small definition is a ray. This is also intuitively very clear. So this ray is, you instead of taking a unit vector, you just extend it. So that's the ray which is based at pkx passing through x. So it is nothing but pkx plus lambda times ukx, such that lambda is bigger than or equal to 0. So this you can imagine when I choose lambda equals 1, pkx plus ukx is just the unit vector based out of this point. Otherwise, you just keep on extending all the way to infinity. So that's the ray. So this is the ray through pkx. So ray through x with endpoint pkx. With endpoint pkx. So this is some basic notation. So here's another important property of the metric projection. The metric projection is a contractive map. Is contracting. So what does that mean? That is, if you think of metric projection as f, so fx minus fy, or distance of fx and fy, is less than equal to distance of x and y. So that is what it means to be a map on a metric space to be contracting. So just write out that. So f of x, distance between f of x and f of y. So here f being like this pk dot. So this is less than equal to distance between x and y. And this is true for all xy in Rn. Okay. So here also the proof, a lot of these proofs actually involves your intuition from Euclidean geometry, just like we used isosceles triangle in that case to prove uniqueness. So here also visually it is very clear what the proof should look like. So first of all, assume that x is not equal to y. Of course, if x is equal to y, there is nothing to prove. Both sides are 0. Yeah, assume, actually you assume something a little bit more than that. Assume pkx is not equal to pky. Because if that is the case, also this is obvious. Left hand side is 0 and right hand side is positive or non-negative. So anyway, we can assume this and define v as the vector pkx minus pky. So this is not equal to the 0 vector. Okay. So now what we are going to do, we are going to look at, so let's say this is the hyperplane, which is orthogonal. So you have pkx here. I'm not drawing k, and x is here. And this is the hyperplane, which is, so this you can treat as that vector A. When we are defining hyperplanes, we had A and a scalar B. So here you take this as the vector and define the hyperplane based on the fact that pkx is on that hyperplane. So my claim is that x minus pkx v is bigger than or equal to 0. So what is x minus pkx? That is this vector right here. And I'm claiming that this vector v, which we took as pkx minus pky, is in fact more than 90 degrees. So it is somewhere in this direction. It is going in this direction. So how do we show that? Yeah, so for that, I want to first show that, yeah, right. So one thing to notice is the whole of k is in this side, right? And that's because this is the closest point. So if you take any other point, so if it was like passing over, like if k was passing over to h, there is a way to find a closer point. How so? So if you have a point here, you just join this line. This is an acute angle. So yeah, so this distance will decline as you go from here to here. So the distance will decline. So from what we saw in the previous theorem, because pkx is the closest point in k to x, so what that means is if you take any element of k, x minus pkx, the angle of that will be more than 90 degrees. So, but we want to show that for v also. Okay.
That vector will also be in the convex.
Yeah, that vector will also be in that convex set. So let me draw that picture. So I have pkx here. Pky will also be somewhere here, right? Pky is an element of k, so it will be somewhere here. So you have this vector x. And what I will do is join these two lines and then draw these, the hyperplanes here. So there are precisely two hyperplanes and these endpoints, pkx and pky, and they're not equal. So there is a unique way to do that, orthogonal to this vector which joins pkx, py. So orthogonal to v, you can say. So this is my vector v. So I defined it as pkx minus pky. So its direction is this way. So this is my vector v. So what I do know is x minus pkx dotted with v is bigger than equal to 0 because v is kind of pointing this way, the way I have defined it. So it's bigger than equal to 0. And similarly, you will have y minus pky dotted with v is less than equal to 0. And that is primarily because the direction of v is this way, but the logic is still the same. You have y and pky is the closest point there. Yeah. Now the line segment joining x and y, so which I'm denoting by this, meets these two hyperplanes, meets the two hyperplanes that are orthogonal to v, hyperplanes that are orthogonal to v, and that go through pkx and pky respectively. I mean, I have already drawn the picture. I'm just writing that out in words. Through pkx and pky. Respectively. So just look at this picture. So I have x here, pkx here, pky is here. So these are the two hyperplanes we're talking about. Looks like a line, but in general, you're just taking things that are orthogonal to v and pass through pkx. And here you're taking all those points which are orthogonal to v and pass through pky. Okay. So y cannot belong to this region. So y has to be somewhere here because y minus pky. So this angle has to, this is 90 degree, this is 90 degree. So from this description, we have that this has to be, these both angles have to be bigger than 90 degrees. So the y has to lie outside of this region. Otherwise you'll get an acute angle. So that tells me that I have this strip, equidistant like lines here. And the distance is distance between pky and pkx. And x and y have to lie outside that on both different ends. So clearly this tells me that v, norm of v, is less than equal to norm of y minus x. So that's the end of the proof. So yeah, just go back after class, go through this. Like it's basically Euclidean geometry. You're just reducing the problem to a two-dimensional space so that you can do your like standard classical Euclidean geometry. But yeah, you just have to realize that pkx, pky both lie in K. Yeah. All right, so that's one.
Sir, isn't a general least distance function contract like it is also a contraction, right?
Is that so? So let's see. So if you define distance x to a, that's
Yes.
infimum of all these dxy says that y belongs to a. So we want to say distance of x1 and x2
Is greater than or equal to.
I guess it would be twice of the distance of x.
Yeah, I don't think so. Here,
if we use triangular inequality, then we'll get two there.
Yeah. If you use triangle, I don't think it should be possible. Is because we can always change the metric and twist it in such a way that these things come in between. So yeah, without that factor of 2, I don't think that should be possible. Yeah, but let me think about it later, yeah, maybe email you an answer. But yeah, like someone pointed out, you will get a factor of 2. So here we are very much strongly using the fact that things are convex, and you have this structure on your metric space, linear structure, where you can immediately say that x and y are outside of this. Like there is some sort of symmetry in here. You're able to translate this using some action of r, and still compare the distance to at this level. Okay.
Yes, sir.
Okay. So the next lemma is, again, these are all preparatory lemmas towards the representation theorem, we should not forget. But anyway, this is giving you the lay of the land. So we have this metric projection, which is defining like for any given x and Rn, finding out the closest point in K to that point x. And this property we saw was the contracting property. And the next thing is, if we have a sphere containing K remember is a non-empty closed convex set. That has been our umbrella hypothesis. So let S be a sphere containing K in its interior.
So that factor of 2 may or may not come, I think, using triangular inequality.
Okay, so how about we talk about that after class? Like we finish this discussion, and then we'll come back and talk this through.
Okay.
All right. So here, let S be a sphere containing K in its interior. So essentially, you have a big sphere. This is that here. Of course, that also means that K is a compact convex set. So you have a K here. Then what it is saying is, so what is PKS? So it's the image of S under this metric projection. So it is saying that any point in the boundary is essentially coming. Of course, if you have any point on the boundary of the sphere, there is definitely some point here which corresponds to that. Like there is a closest point. But here we are kind of talking about the converse. You're saying that give me any point on the boundary of this convex set. I can find a point on the sphere such that this will be that like this X will be the closest point to this Y. So writing in words, for X belongs to boundary of K, there exists Y in boundary of S such that Pk of Y is equal to X. So that's what it is claiming. And in this proof, we'll use some of the things you have done in analysis too about metric spaces. So this fact is, of course, very clear. PKS belongs to boundary of K. That is clear. That means I take any point here and I look at the closest point that has to lie on the boundary. So that is fine. Okay, let's see. Can we give a... Yeah, right. Because like if you join those 2 points, it has to intersect somewhere on the boundary. So if the point were in the interior, then you would have other points which are closer actually. So yeah, PKS is contained in boundary. So the converse is the one that needs a little bit of work. Now, let X belongs to boundary of K. So for I in N, we'll define a sequence of points. So choose Xi in interior of S minus K. So K is closed and S is such that K is completely contained in the interior of S. So interior of S minus K again will be an open set. It's intersection of 2 open sets. So you choose this such that Xi minus X. So distance between Xi and X is less than 1 over I. So effectively you choose somewhere in this like annulus type of region, you choose a point which is very close to X. So Xi minus X is less than 1 over I. So as P is contracting, as Pk, this metric projection or the nearest point map is contracting. So what do we have? X minus Pkxi, which by definition is Pkx. So X is equal to Pkx, right? Because X lies on K. So there it is, P is behaving like the identity map. And this is less than equal to distance between X and Xi, which by our choice of Xi is less than 1 over I. Okay, so now you can imagine I'll take a limiting procedure of this sequence. But before that, I need to find points. So this was points in the interior of S minus K, but I want to find points in S, on the boundary of S, in fact. So the ray RKXI, so recall what was this ray? It was essentially you look at PKXI, which is close to X, but not quite X. And you have Xi here, ray is this point going off to infinity. So this ray meets S in a point, meets S at say Yi. So you have this thing. So this ray better intersect at some point at Yi. And there, pk of yi is in fact equal to pk of xi. So this is a fact. Actually, if you take any point on the ray, the closest point on the convex set will be the same point. So for that, you can use similar triangles. You can just say, okay, I have this k, and I have x here and another point y here. So my claim is pk of x is same as pk of y. And if not, if y kind of connects here, then you can join these points. Yeah, and this whole line will lie in here. And this side is bigger than this side. Sorry, this length is bigger than this length, simply because that is the definition of pky. Which means this part will be bigger. Yeah, and then you can draw a parallel line here also. Oh, the picture is getting muddled, but so this was x, this was y. So let's say this is pky. So by definition, this length has to be bigger than this, because otherwise this would not be pky. So you draw similar triangles here and a parallel line also here. So then what you will conclude is, since this is bigger than this segment should also be bigger than this segment. And because of that fact, using similar triangles in this direction, what you will conclude is this line is in fact smaller than this line. Or you can directly do that actually, because this is less than this. This must be less than this. But this point actually lies on the convex set, because these 2 points lie on the convex set. So the line segment also lies there. So anyway, so you can prove that if you have a ray, then this function is actually constant on that ray. So if you join like pkx and x, so whatever ray you get, the function pk, the metric projection, is actually constant there. So that's what I'm using here. So hence, what I have is x minus pky vec. So recall here, what did I have? Pkx minus pkxi vec. But pkxi vec is pky vec. So I wanted points on the sphere, which will project down to that particular point x. Okay, so this is less than 1 over I. Now we know that sphere surface is compact. So every sequence has a fill in the blanks subsequence. Can someone fill in the blanks? So yi is a sequence of points on the compact set.
Convergent.
Exactly. So on the compact set, which is boundary of the sphere. So this implies there is a convergent sequence. And let's say it converges to y. So there is a convergent subsequence. We can just abuse notation and say the same yi, so which converges to y, belongs to boundary of S. So for that also these inequalities will hold true, and taking limits, what we see is x is equal to p of ky. So that finishes the proof. So anything on the boundary of the convex set essentially is a projection of something on this big sphere. Okay. So it looks like we will be unable to finish representation theorem 1 today. So as I had expected, it will spill over to next class. Okay, so essentially we have set up all the things we need. Next thing we'll be talking about is support properties of convex sets. The thing I had said about intuitively being clear that any convex set is at any point you can find a supporting hyperplane, that will prove that at any point. So if you have K, so let me just mention the next lemma we will be doing. So if K is non-empty, closed, and convex, non-empty, closed, convex set in Rn, and X is in Rn minus K, so outside of K. So the hyperplane H through PKX orthogonal to UKX supports K. This will actually, in fact, be immediate. We'll start off with this lemma in the next class. So if this is the convex set and I take arbitrary X and I have this PKX. So if I just take things that are perpendicular to this vector and containing PKX, that will be a supporting hyperplane. In fact, we have used this fact in the proof here. So to show that whatever hyperplane we got here, the angle will be bigger than that. But yeah, we'll revisit it. So let's spend a minute on the statement of for general metric spaces. So you have a set A, let's say a compact set A, and you have defined D function f of x is nothing but distance of x to A. So the question is whether fx, distance of fx, yeah, so that is the problem, right? So
that is uniformly continuous.
So fx is equal to y such that, I mean, so fx is the closest point. So I should say closest point in A to x. And what we want to say is distance of fx and fy is less than equal to distance of x and y.
So that's wrong. Like if we take a circle and take any 2 points inside it, then obviously the projection points will be farther than those 2 points.
Okay, I see. So yeah, right. Your set is in fact just the circle
Just the circle, yes.
Without taking its interior. That's
So
right.
convexity is important.
Perfect. Yeah, great. Yeah, so convexity will always make sure that you fill in and you are going outside, so that whenever you're projecting down, it's like in perspective, it is kind of coming down like this. But yeah, very great example. So actually, since I have not seen your faces, it's hard to recognize by voice. So who gave this answer?
Aprameya.
Aprameya. Okay, great. So I hope this clarifies. So we are strongly using the convexity here. So this is metric space. It's not good enough, but a factor of 2.
We can take that distance of x comma f of x less than equals to distance of x comma y. Similarly, distance of y comma f of y less than equal to distance of x comma y. Then add these two inequalities, and after that, using a pair, using triangular inequality, we can get the factor of 2.
But that also, from this example, I'm a bit skeptical, simply because what if I change the size of the circle?
I think distance function is a contraction, but not the projection function. Like distance, the subtraction of the distances, least distances will be
okay. I see. So I think you mean just this d of y.
Yes. This is a contraction. Yeah. So this is less than or equal to dx comma a minus dy comma a is less than or equal to.
Yeah, right. So dx comma a and dy is less than equal to d 2 times
x comma
y. Yeah.
But not the projection points.
Yeah, right. So you have to remember the projection point is, in fact, so there pk was a map from Rn to Rn. I specified k, but k was a subset of Rn. It is not a map from Rn to R, for example. But the distance function, this function, which sends Rn, so vector x to distance of x and pkx. So this is precisely distance of x to k. So this function is a map from Rn to R, and there you will have that, you can use the triangle inequality. Okay, so any other questions? Okay, if not, I think we have gone way past time. So we'll continue this, and hopefully at least next time we should try to finish representation theorem 1. And I think next week we'll not be able to come back to LP. We'll have to postpone it until after we finish this convex geometry stuff. Okay, so see you on Tuesday. Bye-bye.